we'll give you a brief demonstration of the Control System Designer tool in Matlab. To start, let's talk about a problem that we want to design a controller for. So on the screen here, you can see a standard feedback diagram. Let's suppose our g of s is given by the transfer function here. H of s is just 1, and we want to design a controller that is a proportional integral controller to achieve a 0 steady state error for a step input and less than or equal to a 5% overshoot for that step input. So suppose we've gone through the math and designed that controller by hand, and we get the following result given here. And now we want to see how that controller does more accurately with the Control System Designer. So going over to Matlab here, we can first enter those transfer functions. The easiest way to do that is to first set up our symbolic variable for s, like that. Then we can enter in our transfer functions. So we have g is 1 over s plus 2, s plus 3, s plus 4. And, oops, we need to put in the multiplication signs there. H is just 1, we'll put it in there. And let's hold off on C for now. We'll enter C manually in the Control System Designer, just so you can see how that works. So first, it's useful to orient yourself to the inputs that Control System Designer uses. So if you look at Help, Control System Designer, I'm going to hit Tab so it auto-completes there. You can see there's a bunch of different options. So it's designed to operate on the same kind of loop that we have for our problem. You can either give it just G, and then it's essentially going to assume that C and H are 1, or you can give it G and C, or you can give it G, C, and H, or G, C, H, and F. We're not going to worry about F here. The format that you'll want to use typically will be with G, C, and H, so get in the habit of that. So to run this, we'll say Control System Designer of G. Our C, we're just going to put in 1. We're going to add that in and edit it manually in the Control System Designer. And then we'll put in H, which is also 1 in this problem, but we'll put in H symbolically since we defined it. Then we just hit enter. This usually takes a little while to start up because there's a lot of computations it has to do. And it pops up with this window. I'll make this a little bigger. There's a lot of stuff going on here, and we'll walk through it in a moment. First thing I'm going to do, though, is go to Preferences and Options, and then select 0 pole gain. This way, the format of the transfer functions and the controller we enter will look a lot more like the ones that we're designing by hand. So we'll hit Apply and OK. So you can see here on the left, this is a Bodhi plot of your loop transfer function. We're going to ignore that for now, so I'm going to make that smaller so we can focus on the root locus and the step response. So you can see here what you would get for this system if our controller was just 1, just a proportional controller with a gain of 1. You see the root locus plotted here. You see these purple things. These are the closed loop poles that are associated with your selection of the gain, k. In this case, it's 1. This will show you the step response. We can add a couple useful features to these plots. If we right-click on the root locus, we can add a design constraint. We can say New. And for this problem, we wanted an overshoot of 5%, so we can enter that, and it'll show you those lines here. So we want our dominant second order system to have its poles within this cone shape region if we want the overshoot to be less than or equal to 5%. On the step response, we didn't have design constraints for this problem for a settling time, but we could put in something just to kind of get a sense of what that looks like. We can show some of the characteristics. So we could show, for example, what the settling time actually comes out to. You could put in other ones as well. Okay, you can see here, if you look closely at the end here, let's put in the steady state value here. It'll show you the steady state value. If you click on it, show you the final value is 0.04. That's nowhere near 1, which is what you would need for a steady state error of 0. So we definitely need an integral controller here. So if we click on the root locus, or click on the root locus here, you can say Edit Compensator, And then we will put in the components of our compensator. So what we had designed was that we have a pure integrator. We also had a zero, a real zero, with a value at the location was at minus 0.25, corresponding to s plus 0.25, and our gain was 0.375. So now we've entered exactly the controller that we designed, and so we can close this out. And you can see now that our root locus has a pole right at the origin. That's our integrator. It's got this little zero right there, and the closed loop poles have moved a little bit. If you look now, you can see that our steady state value, our final value, is 1. So our steady state error is indeed 0. You can see, though, that our settling time is quite long, close to 1,000 seconds. Now, that wasn't something that we were designing for, but we do have a little bit of leeway in terms of our desired overshoot, which was 5%. So you can now fine-tune things by moving. You can click and drag these little magenta dots and move them along, and they will travel along the root locus. That corresponds to increasing values of k. And so you can see in our step response what's happening. As we increase k, the settling time will go down, and the overshoot hasn't started showing up yet, so we can keep going. Now, in principle, once we get to this line here, our overshoot should be 5%. But you can see that it's not actually hitting an overshoot of 5%. That's because we do have an extra 0 here, and there's a closed loop pole in there as well. So if you want, you could fine-tune things a little bit further and see what happens, if you move this 0 out. And that gives you a little more leeway to increase the gain a little bit further. And so through that process, you can see that we're able to improve the performance of our closed loop system pretty efficiently. We got it down from 1,000 seconds settling time down to here, close to 4 seconds, and we're still at 0 steady state error and hardly any overshoot. That's all for the control system designer tool for now.